So, in the previous module, which was variable selection part 1, we have learned 3 different methods of variable selection, namely the backward elimination, forward selection and the stepwise selection of variables that can be included in a regression model. The basic idea is to keep the significant independent variables or regressor variables and to remove the ones that are insignificant or the ones that do not add much information to our model. In this module, we will learn the different criteria that we use to keep the regression model where the variables that are selected are significant and the ones that are insignificant are removed. Sometimes while fitting a linear model, we have a lot of predictor variables, but we wish to include only the statistically significant ones in our model. So, while fitting a model to a data set, it is of utmost importance to decide on which predictors should be included and which ones should not. And to that end, there are several criteria based on which we can make a selection of predictors. And we will dedicate this module to the study of these criteria and their mathematical aspects. In a regression setup, the model building is a multi-stage process. It mostly consists of the following steps. We first start with the collection of data on response and explanatory variables, and then we reduce the predictor variables to the ones that are significant, and then we perform model refinement and selection, and then we validate our model and come up with the final model which is the best for fitting a regression model on the response and the explanatory variables. Now, what is the need of variable or model selection? We need to select different models for different purposes. In case we wish to use a model for prediction, then including only the significant predictor variables is preferred. When we wish to use a model for prediction, we only wish to use the significant predictors because these are the predictors which will actually give me some information, some significant information about the response variable. However, if there is an insignificant variable which is included in the prediction model, then their inclusion only increases the number of parameters that we have to estimate and not add significantly to the information on the response variable, which is our underlying idea. If our purpose is to develop a descriptive model that explains the nature of response, then adding as much information as possible is favorable. When we have a descriptive model, in that case using more number of predictors makes more sense because every little ounce of information that we can gather about the response variable is useful. In such cases, if there are insignificant predictor variables included in the model, which also provide us with some amount of information about the predictors, about the response variable, then even that helps. So, in case of descriptive model, we add as much information as possible, and so variable selection is not mostly performed. In order to perform model selection, we need to employ one of the following possible criteria. When we wish to fit a prediction model, in that case we need to keep in mind one or more of these selection criteria in our mind in order to remove the redundant variables and retain the ones which are important. The first criteria is R square, although this criteria is sometimes used. When we fit a regression model to the data in R, we have seen using the ln function, the summary of the function will give us the R square values, and we will also notice that as we increase the number of predictors in the model, the R square values increase. Although this criteria is not a very useful one because it always increases with the increase in number of explanatory variables in the model. Whether the included predictor variables are all significant or not does not count when it comes to R square. As long as we keep increasing the number of predictor variables, the R square is going to increase. In other words, a model which contains 5 predictors, 3 of which are insignificant, would still have an R-square for the 5 predictor model greater than the one for the 2 significant predictor models. Thus, basing our criteria only on R-square would mean that we will end up selecting a model that has a large number of insignificant predictors and a large number of redundant parameters. So, a betterment of the R-square criteria is using the adjusted R-square. A better choice than R-square because the adjusted R-square increases only if the new term involved improves the model more than would be expected by chance, unlike R-square, which increases with the inclusion of new variables even if they do not play a significant role. We will see later on how the mathematical form of adjusted R-square actually explains how adjusted R-square is a better choice than R-square. Then the third criteria that we can use is the Mallows CP criteria, and then we have Akaike's information criteria, or most commonly known as AIC, and Schwartz Bayesian information criteria, or commonly known as BICs. Now let us first focus our discussion on Mallows CP criteria. The CP of Mallows CP criteria is defined as a criteria to assess fits of model when model with different number of parameters are compared. The mathematical form of the CP is given by residual sum of square p divided by sigma hat square minus n plus 2p, where residual sum of square p, or RSSP as written here, denotes the residual sum of square from a model with p number of predictor variables, n is the number of observations, and sigma hat square is the error sum of squares. So, how is this criteria used? We have looked at the mathematical expression for Mallows CP criteria, but how do we use the criteria? If the model with p parameters is the best fitted model, then the Mallows CP criteria will be close to or smaller than p. The method of identifying the best fitted model is by plotting CP against p. Now, Mallows CP for ordinary linear regression. In case of ordinary linear regression, Mallows CP criteria is based on estimating the mean square error of the estimator beta hat, which is given by beta hat subscript p equals x p prime x p whole inverse x p prime y, which is given by expectation beta hat subscript p minus beta whole square, where beta hat subscript p minus beta is the error. We take the square of that and the expectation. This means square error can be written based on the residual sum of square for the model with p parameters. So, the residual sum of square p equals summation I equals 1 to n yi minus xi beta p hat whole square can be written as y minus xp times beta p hat prime y minus xp beta p hat, which equals y prime times I minus xp times xp prime xp whole inverse xp prime y, where In is an n by n identity matrix. Now, to complete this proof, we use the following result from quadratic forms. We know that expectation y prime ay equals expectation y prime times a times expectation y plus trace of sigma a, where sigma is the variance matrix of y. The next criteria that we use to select variables for a model is the Akaike's information criteria, or the AIC. If there are p potential predictors, then there are 2 to the power p possible models. We can fit all these models and we can choose the best one using several criteria available to us. One such criteria is the AIC. In general, the AIC of a model is given by 2 times log likelihood. In general, the AIC of a model is given by the mathematical expression AIC equals negative 2 times log likelihood plus 2p, where p is the number of parameters in the model. The next criteria that we use to select variables for a model is the Akaike's information criteria, or the AIC. If there are p potential predictors, then there are 2 to the power p possible models. We can fit all these models and we can choose the best one using several criteria available to us. One such criteria is the AIC. In general, the AIC of a model is given by 2 times log likelihood. In general, the AIC of a model is given by the mathematical expression AIC equals negative 2 times log likelihood plus 2p, where p is the number of parameters in the model. So here is how we can use AICs. We have seen this example before where we had used the step function on the LM object regression to obtain our set of significant predictors. So again here we are using the state data, we are putting it in a data frame. We have life expectancy as the response variable and we have population, income, illiteracy, murder, HS graduation, frost and area as the predictor variables. And then as we had seen before, we had selected the significant predictors from the step function in R by looking at the AICs of each of these models. I will not go into the detail of the stepwise backward elimination method of obtaining the set of significant predictors, but I will only mention that in each of these cases, when we selected the significant predictors, we had used the criteria of AIC for selecting the significant ones. In the R output, we can see that there is a stepwise selection of variables into the model. We started with the entire set of predictors and then removed the insignificant ones, just like the way in backward elimination theory. At each step, we compared the AIC as indicated in the output of the model containing predictors, and the one with the lowest AIC is the one that gets selected. In other words, the model with the highest AIC is discarded. In the first step, if you look at the output, we start with the whole model which contains all the predictors, which happens to have an AIC of negative 22.18. R now fits the model by removing the predictors one at a time and fitting the model after each removal. We see that if we remove the predictor area, the AIC is the highest and hence remove area from the model. Now the maximum likelihood estimators. In the formula for AIC, we have a term which is the likelihood function of parameters involved in the model and evaluated at the maximum likelihood estimators. If the model is correct, then the log likelihood of the two parameters are beta sigma is given by log L beta sigma given x and y equals negative n divided by 2 times log 2 pi plus log sigma square minus 1 over 2 sigma square y minus x beta square. As you can see, the first term in the above expression is independent of beta. Hence, the MLE for beta is the same as the least square estimate for beta, because if you look at the second term, it is y minus x beta square or y minus x beta prime y minus x beta, which is the least square that we use to obtain the estimate of parameter beta. So solving the score equations, we obtain from the likelihood function, we obtain beta hat MLE, which equals beta hat, and we obtain sigma hat square MLE, which equals 1 over n times residual sum of square of the model P predictors. We see that for the multiple regression, the AIC is given by AIC equals n times log twice pi plus log residual sum of square for model with P predictors minus log n plus 2 times n plus p plus 1. If sigma square is known, then AIC equals n times log twice pi plus log sigma square plus RSSP divided by sigma square plus 2p. Now using adjusted R square. Recall that R square can actually be written as 1 minus residual sum of square divided by total sum of square. Adding a variable to the model can only decrease the residual sum of square, so only increase the R square. So R square by itself is not a good criteria because it would always increase with the inclusion of added predictors. Now here is an expression for the adjusted R square, and this is how it actually counters the effect that R square has with the inclusion of a parameter into the model. Adjusted R square is given by R square subscript A equals 1 minus residual sum of square divided by n minus p over total sum of square divided by n minus 1, which can be written in terms of R square as 1 minus n minus 1 divided by n minus p times 1 minus R square, or which equals 1 minus sigma hat square of the model divided by sigma hat square under the null. So, under adjusted R square, when adding a predictor will only increase R square subscript A if it has some value, that is, if it is statistically significant. And minimizing the standard error for prediction means minimizing sigma hat square, which in turn means maximizing R square subscript A or the adjusted R square. Now, let us take a look at the malloc CP and adjusted R square for the selection of variables in the state data. We will use the leaps function in the leaps package. The default for the leaps function is the malloc CP criteria. So, we include the data state by writing the function data state and we put it in a data frame. Then we write REG as the LM object of regressing life expectancy on all the parameters, on all the predictor variables that are included in the data set. Then we use the leaps function and call that M. So, M equals leaps, X equals our new state and Y equals state data with fourth column of the state data, which is our response variable. So, as you can see here, we have used X equals new state, where new state is the data set which contains the state data set only the columns 1 through 3 and 5 through 8, and these are the columns that contain data for the regression predictor variables. So, this is the R output. In the above output, we can see an array of true and false. Their interpretation is as follows. In the first 3 rows which are included in the output, we see 1 true and the rest are false, meaning the model contains only one predictor, and the others are false, meaning the model contains only one which has true and the others are not present. Once the reader performs the leap function, they will see that the entire output gives you all possible model that we can create using all the predictor variables in this data set. So, in total there are 55 models, although I have not presented the entire output here, but there are 55 possible models taking all the possible combinations of the predictors that are available. And for each of them we obtain the malloc CP. As we have mentioned before, the model with the CP very close to the number of parameters in the model P is the best model. In our current case, the best model is given by the model that has CP very close to 6. Now, let us see which model the adjusted RA square criteria selects. So, here in the R output, we have the CP calculated from the 55 models by taking all possible combination of the predictors. So, in each of these models, the reader can go back to the previous output and see how many predictors were included. For instance, the first model here contained only one predictor, only one true was present and all the others were false, which means this model contained only one predictor. However, corresponding to the first model which only had one predictor, the CP is 16.12. So, CP is not very close to P. So, this is not a very good model. So, the reader can actually go from each value of CP and compare it with the corresponding model and see in which case the number of predictor in the model is very close to the CP obtained for that particular model, and that model will be considered the best model. Now, let us see which model the adjusted R square criteria selects. So, if we use leaps function again, the default criteria is malloc CP criteria. However, we can mention method equals ADJR2, and that will use adjusted R square as the criteria for selecting the models. So, after we use the leaps function with method equals ADJ R2, we can obtain all the adjusted R squares for all possible 55 models. Now, in order to see which model the adjusted R square chooses, we can summarize the best models in the Leaps object using the function max ADJR. And after using this function, we can see here that the first model output here contains the predictors 1, 4, 5 and 6, and the corresponding max adjusted R square is 0.713. And for the second model, which contains the first, second, fourth, fifth and sixth predictor variables, the corresponding adjusted R square is 0.706. And we can see that the highest is 0.713, which is for the first model, which contains the predictors population, frost, HS graduation and murder. Now, if you go back to the module which was variable selection 1, when we had used backward selection, forward selection and stepwise regression method, the best model that was selected using the same data set also contained the 4 significant predictor variables, which were the same 4 significant predictor variables that we have selected here. So, we can also use R functions to perform model selection. We can also look at the leverages and see which row of data can be deleted, because outliers also affect the selection of variables. So, we use the REV sort H functions. By H, we denote the hat values of the new state data set, and we use the function REV sort the hat values, and we see that Alaska has the highest leverage and is a potential outlier. So, we can remove that row of data and we can perform the previously discussed variable selection techniques to obtain the significant variable. In this module, we have learnt several important criteria based methods of selecting variables in a regression model. We have learnt the AICs, or the Akaike's information criteria, and we have learnt about Mallow's CP criteria, and we have also seen, using examples and functions from R, how we can use R to use these criteria and select the model which is best fit for a regression.